Good, we are ready to restart. Do you hear me? Thank you. Now we will discuss some of the other attributes that are used by BGP to implement policy in particular. So one of them is local pref. That's a priority field that is used by BGP routers inside the domain. So it's an attribute which is added to the BGP updates and is transported by i-BGP but not by e-BGP. Okay, I keep muting for some reason. Do you hear me now? Yes. Yeah. Okay. So here I'm showing an AS, AS4, that pairs with two other ASs, 2 and 3, but for some reason doesn't like the link between 2 and 4. Perhaps it's a very expensive link, perhaps it's a low quality link. So it prefers to use AS3, or perhaps it doesn't like AS2 at all here. Nonetheless, through the desire to get as much reachability information as possible, we will still keep the information here. But what AS4 will do, for example, at R1, it will set the local pref value to a small value, which means less priority, to the information that is received from AS2, AS1. So this field here will be tagged with a local pref of 50. The other one here, received by R2, will be tagged with a local pref of 100. So other routers in the domain, like R3 and also R1 and R2, will receive both of this information through i-BGP. Then they will compare the two local pref that comes before other criterions like EGP versus i-BGP versus e-BGP. And we will give priority to the highest local pref, which is this one. So even R1 will prefer the route that comes this way here. And R3, of course, will prefer this one here. What would R3 in such a setting announce to R5, to AS5 here? Quick poll. I close the poll in a few seconds. And the majority says B, which is the correct answer. So answer C is not possible because BGP allows only the best route to be propagated. So for the same prefix, the route that would come this way is not preferred. Therefore, AS5 will not even know that this path exists here. So the local pref is a way to really manipulate the AS path, as we have seen when we do policy routing here. So that is exactly what will happen. In BGP, there are probably more than 100 possible attributes, so we will not discuss all of them. The weight is one attribute, which is a priority field given internally in a router. It doesn't propagate even internally in the same AS, but that's a way to supersede the rules that you have. So the decision process is a very rigid mechanism where you prioritize a number of rules. If you want to specifically say for this route or this type of route, I prefer not to do this or not to do that, then you can always manipulate that by putting the appropriate weight. We saw similar use of weights when we discussed SDN, software-defined networking, where we would have multiple rules that apply to packets. Here, it's similar. Another important field that is often visible is called the multi-exit discriminator, the MED. It's also a priority field, but its use is different. It is typically used when a customer like Y has a provider X and is multi-homed. So multi-home means is connected to its provider through multiple access points, which is very often the case, is practically always the case because of redundancy. You don't want to be connected via a single line. Sometimes you're connected via a double line, for example, and this group of lines can be manipulated as one single point of presence. Here, I'm assuming we are really connected at two radically different locations. For example, ASX is a provider that gives service worldwide, and Y is a company that has also presence in multiple countries and connects to X in every country where they have presence. Perhaps also there is an internal route, an internal network that can be used privately inside X, but inside Y. But since you use the service of X, you would like that most traffic goes via X, right? You pay this guy to carry your traffic. So one way to force this to happen is to use a priority field called MED, which is specific to this scenario, where here we see that R3 is directly connected to 10.1, so it will signal this to R1 by giving a lower value of the MED. Now here, that's the embarrassing thing, but this is how things are. Low means preferred here. For preference, that was the other one. Low meant non-preferred here. So here, we're signaling that we are connected to we advertise 10.1 and 10.2, but we give priority in our advertisement to 10.1. Conversely, R4 will also advertise 10.1, but with the reverse priorities. The intention here is to say, I want that the traffic to 10.1 goes via this link rather than this one, because now inside the network, we will have two routes and two next hops to 10.1, one learned from R3, one learned from R1, and we want to guarantee that the priority is always given to the one learned from R3 here, because it has the smallest MED here. Let's check this here. R1 has two routes to 10.2, one via R3, learned over e-BGP, one via R4 and R2, learned by i-BGP from the viewpoint at R1, with MED equal 10. Which one will the decision process at R1 prefer? I close in a few seconds. And the majority says A, which is the correct answer. To know that, you have to look at the decision process, and we see that the decision process applies MED before the decision whether e-BGP should be compared with i-BGP. So in this case, this will clearly say that R1 prefers this route, which means that the packet that goes to 10.1 will go this way, and the packet that goes to 10.2 will go that way. So the provider, ASX, will do cold potato routing and will keep the packets internally as close as possible to the destination, which is the expected behavior if you pay X for giving you a service. Okay. Of course, we can check that the use of this is to be able to have redundancy. What happens if, for example, router R3 crashes, this one here? Of course, if 10.1 is attached only to R3, then there's nothing you can do. But here, presumably, there is some redundancy inside the network. Perhaps there's an internal path, low capacity, that you would not like to use unless strictly necessary. In this case, you will use it. R1, when it sees that R3 is dead by, for example, the keep alive mechanism, will clear all the routes it has learned that comes from R3, for example, those two routes here. Therefore, in its decision process, it will have only one route to 10.1, that was the one learned from R2 and R4, and it will select now this one as best one, which means that packets to 10.1 will now be routed by R1 to R2, and presumably inside ASY they will find a path here. So this MED mechanism allows to do two things. It allows the client to be dual owned, to have 2 points of connection and use the closest link, but still use the other links as backup, which is of course a constant thing we would like to do with BGP. When designing the policy, we always want to have such possibilities here. So we've seen two fields, local pref versus MED. Local pref is used inside an AS to propagate the AS path preferences, and it is really a field that has an important role in implementing the policy. MED is used in a more specific case when we have essentially dual homing. And there are many others that can be used, but we'll not go through them. Before moving on to the other aspects of BGP, one more quiz. What happens when a BGP router loses its best route to some destination here? Right? Quick poll. I close the poll in a few more seconds. And the majority has the correct answer. This router does not have a route anymore, but had informed the other routers of this. Remember, with BGP, we inform only about the changes. There is no mechanisms for other routers to at least quickly learn about the change, other than having B send an explicit withdrawal message to all peers to whom it had sent this route. Now BGP is saying, I don't have this route anymore, which is the case here. If AS4 had passed it along, then this prefix is no longer reachable. Of course, we can reach the destinations via another prefix, but this one does not exist anymore. So this is exactly what will happen with BGP. Because of that, that leads to potential problems. The problem is called route flap. So now let's discuss some of the other aspects of BGP that are, for example, due to the propagation, the following of withdrawal and updated. In other routing protocols where state is periodically refreshed, this problem does not occur. But BGP does not do refreshes. Instead, it does explicit addition or deletion of routes. Now, it happened in the past and is likely to happen again in the future that BGP routers, well, a router, in particular, a BGP router is like a big computer. And like all big computers, it does all the nasty things that computers do. In particular, it can have bugs. And one nasty type of bugs is when the BGP process crashes for some reason. And then because you have a smart computer, it automatically reboots and restarts. And if the problem that caused the crash is still present, then it may crash again. So you can have, and you had in the past, examples where a BGP router crashes, comes up again, announces a number of routes, crashes again. If that happens, the immediate neighbors of this router will discover that this router is dead, will therefore withdraw all the routes that they had learned from these routers, in the worst case. And as soon as the routing process comes up again, we'll learn them again. So we will have oscillations where what is called a flap. A flap is a route that is successively withdrawn, updated, necessary. Of course, that causes a lot of work to the routers, so it is, in some sense, similar to a denial of service attack on the routers here. So one optimization is to put some damping, avoid that this happens a lot. So the current solution to that problem is that every route is associated with a penalty. And I'm showing here an example. The x-axis is time, and the y-axis is the value of the penalty associated with a route. So every route that's in the RIP-in is associated with a counter called its penalty. Assuming the route is withdrawn here, then updated again, whenever there is a withdrawn following by an update, the penalty is increased by some fixed amount. Then, so there was a withdrawn followed by an update, so the route had a penalty here. Which means that when a route is withdrawn, it is in fact not withdrawn from the adjacency RIP-in, it is maintained, it is kept here, but marked with a flag that says this route is invalid. Then if nothing happens, this penalty decays exponentially. So it decreases. Now assume this route, which is a flapping route, is again withdrawn and updated, so its penalty increases, then it decays, then it increases again. Then there are two thresholds, the suppressed limit and the reuse limit. When the value of the counter associated with flapping of this route increases the higher threshold, the route is declared invalid, it is ignored. So this route is suppressed. If so, even though it is present, it is not considered and they're not propagated, therefore, by the BGP routers. Now, hopefully, sooner or later, the routes will, nothing happens, the decay occurs, but I'm assuming here it is again withdrawn and updated, therefore the decay will occur. Now, if the problem at the source is fixed, then the decay will continue, but it's only when the decay is below the lower threshold that the route is re-declared valid again. So during all this interval, from T1 to T2, the route does not exist anymore, which is bad. Perhaps part of the internet is not reachable, but it's better than keeping flapping the route and informing the rest of the world about this route being up and down, up and down. So this is one of the mechanisms that every BGP router must do. We'll see a few others. Another trick that's often used is the private AS number. An AS number is in principle the identifier of a domain, but like for IP addresses, there are private AS numbers. This is used, for example, by EPFL when it speaks to switch. If EPFL is dual homed, then with dual homing, we've seen that BGP provides a very interesting mechanism with the MED to support optimal routing, where the client, EPFL, for example, can indicate to switch that the packets that are in écu blanc should go this way, and the ones that are in Sion, in Valais, should go through another way. So there will be multiple exits, and the use of MED provides a very good mechanism for that. But this works only with BGP. So remember that EPFL does not have an AS number because EPFL is always seen by the rest of the world through switch. For cases like this, we give to EPFL a private AS number. So this private AS number will be translated by the provider when it talks to the rest of the world into its own number. So we can still have an AS number, but a private one, and the private number is not visible to the rest of the world. This is one use of the private AS number when we have multi-homed customers that want to benefit of the features of BGP while not loading the rest of the world with complicated BGP tables. There is another use of the private AS number, which is to avoid the i-BGP mesh. There are cases where the number of BGP routers inside a domain can be very large, and this can be made worse if we don't distribute BGP into OSPF. In that case, we need to run BGP in many, many routers to the point that the complexity of the mesh may be very large. So if you have 2,000 routers in your domain, every BGP router will need to maintain a BGP connection with each of those 2,000 routers. Of course, you can simplify this using the usual trick of computer science called divide and conquer. So you can partition your domain into subdomains and use BGP in between those subdomains. Of course, in reality, there is only one domain. So what you will do is you will give private AS numbers to parts of your domain. You will use formally e-BGP, although it's inside a domain, between BGP routers that are inside subdomains here. And of course, when you talk to the outside through the true e-BGP, you will need to translate the private AS numbers of each of those subdomains to the only AS number that is known to the outside here. So this is a very convenient trick to make a large domain tractable by dividing it into subdomains. Here I'm showing only one e-BGP peering inside the domain. Of course, this is not survivable. We need more redundancy, but the drawing will be more complicated. So all the goodies that you have with BGP, you can use them here. Of course, it's a bit complicated now in terms of terminology. We have e-BGP inside a domain, but because we virtually have different domains. So that's one mechanism that's called a confederation. This domain is itself a confederation of private domains. For some reasons, there are other mechanisms that are used for avoiding the BGP mesh. It's called route reflector. A route reflector is a similar thing, but if you don't like the idea that you use e-BGP inside your domain, another proposal has been done, which consists in clustering the routers. So functionally, it is the same, but from the details and the software, it is different. So you elect inside a cluster one or two route reflectors, and those route reflectors, they work as post offices to avoid that every router peers with everyone. For example, a router here speaks to the route reflector of its own cluster, and the route reflector is meshed with all the route reflectors of all the clusters here. So it is like a confederation, but it doesn't use the concept of virtual AS and virtual AS numbers. For some reasons, both exist. As I mentioned, when different systems with different operators interconnect, they interconnect on links, but also very often on interconnection points, IX, May West, May East in the US, in Switzerland, where Swiss IX. So those are domains where multiple operators connect. And we have seen that policy routing may, in fact, incentivize operators to connect to as many operators as they can. So here is what happens in one of these interconnection points. You have multiple domains, large number. Here I'm showing 4, but in reality, there's a large number of them. And that creates a same problem as we had inside BGP, which is an e-BGP mesh. All the routers that are that are in the same, so there's one router for Swisscom, one for Sunrise, one for Switch, one for Telia. So each of those must connect to each other. And this may be a very large number. Typically, it can be up to 100 or several hundreds of routers. So instead of requiring that everybody interconnects to everyone, as a service, the provider of the interconnection point will typically use what is called a route server. A route server is a BGP router run by the interconnection points that is used as a post office by all the routers here. So instead of peering with everyone, they appear with a route server. But this route server doesn't belong to any specific domain, but it helps the exchange of information here between different domains. Route servers are very visible because typically it is via route servers that we learn information about the internet. They are, of course, points that know everything about all the interconnection, and many route servers agree to make it public. So this is through the route servers that we learn a lot about the information of the internet today. A few words about security. In everything I've said, we trust the information we receive. So what happens if ISP3 on this example is malicious? So the example I've shown is a simplified example of something that really happened. For example, there was in a not so remote path, ASP3 was one country in Asia that did that kind of thing because they didn't like YouTube or some other services that had information that was conformant to the ideology of the government of this country. So one attack against the internet is to inject bogus routes. So assume this guy here doesn't like EPFL and injects to ISP1 a route to two sub-prefixes of EPFL. EPFL is this prefix, 128.178/15, which is made of two sub-prefixes, if we want, 128.178/16 and 128.179/16. Of course, this guy is not allowed to do that. EPFL is here, so only switch is allowed to inject that to neighbors. But this guy does it. It says EPFL is here. It's my customers and it's connected to me. What will happen if C1 here has some traffic to send to EPFL? What do you think will happen? I'll close the call in a few seconds. And a short majority says A, with a large minority saying B. Well, the truth is we don't know, and both are probably correct. We don't know because it depends what is done in terms of aggregation. If aggregation is not done, then we have two routes. This one and we have, this route is different from the global route here. So this one will be accepted, presumably. And by longest prefix match, all traffic to this longer prefix will follow the bogus route. So this hijacking will work. And if aggregation is performed by the destination of these bogus announcements, then we don't know exactly. But what will be is there will be now two competing routes, and probably, depending on the policy and depending on which one is chosen, some fraction of the traffic will be lost and will go to the bogus destination. So this is an example of attacks that exist on BGP. They are not just academic, they exist, they were done repeatedly in the past. So because of those attacks, a number of security measures are done in BGP, essentially three. The first one is a monitoring. The idea of the monitoring is that most actors in BGP are not cheating. So if someone is doing something weird, it will be visible by observing what others think. So for that, we need to say a few words about how the internet is organized. At the top of the internet, there is nobody. So there is nobody running BGP. However, there is an authority that's managing the IP addresses. This authority is called ICANN, which is formerly an American company, but the job of ICANN has been taken by a multinational organization called PTI. So it is this entity which is now managing the address allocations. Address allocation is delegated to 5 regional entities, 1 per continent, 2 for America, North and South, 1 for Asia and Oceania and the Pacific, 1 for Africa and 1 for Europe. For Europe, for us, it's RIPE. So this entity is a European entity that manages the allocation of IP addresses, of other things also, we will see, in particular of public certificates, manages this for Europe. So when Switch receives a block of IP addresses, it receives it from RIPE, for example. Now, RIPE maintains a database of all the blocks allocated to whom, and all ISPs, all ASs can read this domain. So in the case that I gave before, presumably ISP1 that received a block that comes from America, when it was allocated by RIPE, should see that there is a problem and that this route is bogus. So that's the very first mechanism. So it's a weak mechanism, but it's the first response of the ICANN and the registries to this thing. There's a stronger response that is now deployed largely, not everywhere, but largely. It is to sign the route origins here. So for example, when Switch receives this block, it's IPv6 block from the European registry, from RIPE here. At the same time, it will receive not just the block, but it will also obtain a certificate. We've spoken about certificate multiple times. So a certificate, something that is signed by Switch and by RIPE, and that can be published on the registries that we talked before, so that now anybody can verify whether this route record here is really signed and really belongs to Switch. You can try it, you can go online, and you will see whether this block that Switch pretends to have is really validated here. So this requires a cryptographic infrastructure. This is the resource public key infrastructure, which is one of the things that PTI and the registries manage. So they manage the public keys of themselves, of the registries, and all the people to whom they have given the blocks of addresses. And you can go on the internet to check everything. So presumably, ASs will also verify when they get somebody who says, I have this prefix, then you can simply verify that this is signed. If this is not signed, and you can verify the signature because you have the public certificate of who signed this the certificate that corresponds with this block, then you can verify whether the guy who says that is right or not. So this is the second level of security, which is the only one that is really deployed today. Just starting now is a stronger authentication mechanism, which is the validation of the entire path. What we have discussed so far is validating the origination, the fact that Switch is saying this is a block that belongs to me, and this is verified by the mechanism we said before. But then, when this block is forwarded to another operator somewhere in the world, that itself forwards it to someone else by incrementing the AS path. Of course, the AS path might be completely wrong. So another attack on BGP could be not false origination, but AS path manipulation. For example, if an Asian government doesn't like YouTube, they can pass to all ASs around them a path that forces all traffic to YouTube to go through the national company of this country that will, of course, delete all the traffic that goes to YouTube. So you can, by sending also bogus AS path updates, you could give wrong information. The way this is mitigated is by signing not just the origination, but all the path attributes that were done by all the intermediate paths on the way. So this will not, of course, prevent somebody to give wrong thing if that's, but you will know who gave the wrong path. Exactly. You cannot pretend that the path was given by someone else. So this is done by replacing the AS path attribute by an AS path which is signed recursively by all elements. So when you add an element to an AS path, you sign the addition and you sign the things, the signature that you received before. So you have a nested set of signatures that can be unnested when you accept it in order to check whether all elements of this path were signed by who is really saying that they signed. And if something is weird, then you will put an operator on the blacklist and not accept anything of this guy. So this is how security is or will be implemented in the future. Of course, there's a high price to pay. That means that whenever you receive a new message from BGP, you will need to do some cryptographic verification, which is to be compared with the fact that there is up to 1 million prefixes in the world. So that means that the BGP routers need to have very, very good cryptographic processing capabilities. So they need to have hardware assistance to do it, or otherwise extremely powerful processors, which is good news for the router vendors. If you take your old BGP router, probably it will not be able to do the work required by such systems. As I mentioned, by going to route servers, you can gain information on how the internet is. So here's a short map, for example, of the internet of Switzerland. So you see a number 1, 2, 3, 4, 5 peering points where the internet of Switzerland peers with the outside. And you can see here a snapshot of some of the external networks that communicate with, when I say Switzerland, no, the network of Switch. And not Switzerland, the network of Switch, where Switch is the provider of Swiss universities. So you see that it peers with a large number of other networks, even though you could say every country in Europe has an academic network. So this academic network should peer with the neighbor academic networks and perhaps with the European academic network, but that's not the reality. The European academic network is giant. But you see that you peer also with a large number of other things, which is very typical. So in the internet, BGP peerings are usually a lot. So the number of edges in the BGP graph is typically large here. You can go to route servers of some companies. Hurricane Electric is a company that provides us with IPv6 tunnels, for example, but also information for route servers. So if you go there, you will learn a lot on how the internet is from the viewpoint of this company here, which is one of the transit operators in the world. And we can check, for example, the announcement that was provided by Switch, and you see that it is correctly signed and validated. So Hurricane Electric knows that this prefix, which is announced by Switch, is a valid one, cryptographically verified. By going to this provider that I mentioned, you can also see the number of prefixes that they see. And this is a graph over time for IPv4. The y-axis here goes to 1 million, right? So not so long ago, the IPv4 prefixes were a few 100,000 to 300,000. And in a short period of time, it went up to close to 1 million here. It goes up, and it's hard to aggregate because the IPv4 space is exhausted. So we use whatever block of the space we can. And when we do that, it's typically more difficult to aggregate. Remember, for example, the prefixes of IPv4 of EPFL and ETH are not contiguous, and are not contiguous with the other IPv4 prefixes given to customers of Switch, so they cannot be aggregated. In IPv6, in contrast, you see that the numbers, now IPv6 is maturing, so we get to a number which is probably close to the steady state. So we are slightly above 100,000, which is a factor 10 less than IPv4. It's not as good as we would hope. We would love it to be much smaller, and operators are aggressively trying to have social incentives to force all providers to aggregate as much as they can, because by aggregating, you will, of course, reduce the size of those tables here. Voila, that's all we will see today about BGP. Time is too short to start the next module, so we will start the application layer next week. I will take advantage of these few more minutes to discuss a few things about the exam. As we said, the exam will be a take-home exam to avoid you coming to campus at a period where it's not good and might even be forbidden. Who knows if there is a third wave. The exam there are rules set by EPFL on how such an exam will be. And one of the rules is that the exam must be handwritten and scanned and sent back to us. So your homework before moving on is to make sure you have an infrastructure to do this, which may be one of two things. Either you have a printer and a smartphone or a scanner to take a copy of what you will write, or you have an iPad or a tablet or a PC with a touch screen. This will also be accepted, where you can write on your screen with your hand and generate a PDF from your handwritten solution and send it to us. So you will need this to be operational for the exam. We will do mock-up sessions for you to test your infrastructure. So we will do a small example of a mock exam where you will need to very, very short mock exam where you will be able to test whether you have all the infrastructure to be able to do this technique. Another thing is, how will the exam look like? Well, the answer is very simple. It will be very similar to the exams of the past years, even though it will be open book for this year. Experience has shown that open book is a very bad idea for students. In fact, a few years ago, this course had only open book exams. And from the day we introduced the closed book exam with the exam booklet, the grades at the exam were much better, even though the exam didn't change in nature. So there's something very strong I would like to say to you, is that because the exam will be closed book, will be open book, don't change the way you think about it. You will not have the time during the exam to discover something, to learn about BGP and find the solution. So you must know it before. So do as if it would be closed book. And remember, we posted on the website, on the Moodle site of the course, a little thing called the exam booklet, which is all the things you don't have to know by heart, which means the rest you should know. You should not know by heart what is the order of the rules of the BGP decision process. This is in the exam booklet. But you should know by heart that BGP has a decision process and uses only the best route. Right? All those things you should know before the exams, otherwise don't count on it during the exam. So the best preparation to the exam is to do the two exams of the past years. The exam this year will be similar, with a catch. Each of you will receive a different version of the exam. So we will obfuscate the exam such that you will all have different versions. Of course, it's a considerable burden for us, but that's the price to pay for this COVID situation this year. Voila, that's the information. The time for the exam, I'm not sure exactly what the rules of EPFL are, so I cannot give a formal answer to this question. The duration of the exam, but as a rough guideline, it should be a bit longer than what we had in the past years. In the past years, the exam was designed to be done in 3 years. It will be the same this year, will be the same type of exam, also designed to be done in 3 hours, sorry, not years, in 3 hours. But the take-home exam will probably be 4 hours, so that you have a bit more time in case you have any problem with your printer or your tablet or whatever slows you down. So there would be probably 1 hour more. There will be more time, and it will probably be 1 hour more. So you should count on 4 hours. One question is, taking picture with a smartphone okay? The answer is yes, it's one of the techniques. But if you do that, you will still need to be able to scan the thing and sorry, the answer is yes, and then you'll need to find a way to transfer the PDF from your smartphone to Moodle. Voila, so we will talk more about that as soon as we're ready with the mock session. We will post it on Moodle, but I wanted to share that already with you. So if you have any other questions, please use the news group, the forum on Moodle, or contact us, me or the TAs of the course. Voila, take care, stay safe, and enjoy the rest.